9.8 meters per second square. I wrote a minus sign in front. If you take the axis to go upwards, if you take the axis to go downwards, of course it becomes a plus sign. So today we'll move on to vectors. In the handout I distributed to you, if you look at it, there is at the bottom notes, 就是特别讲了关于这个 vector。这 vector 的这个观念是向量，又叫尺量，是非常重要的一个观念。这个观念在Maxwell 以前并没有大家并没有特别注意。我念这个 notes 给你们听啊。James Clerk Maxwell was the first physicist to emphasize the importance of vectors. The following diagram was from a paper he wrote called On the Mathematical Classification of Physical Quantities. Do you see the three diagrams there? On the left is convergence. Convergence 的意思就是向心的，中间的叫做 curve， 右边的叫做 convergence and curve. These three diagrams were from Maxwell's book, or from Maxwell's article. The term curve is still used today. 是一个非常重要的一个观念。现在的这个今天的符号是一个三角形 cross， 是 curve。这个能不能缩小？这个字能不能缩小？
应该可以，我想。
嗯，它有。
它应该有 zoom。
哦。好的 ，OK， 下回再弄好了。convergence 今天已经不用这个 notation， 现在改了名字叫做 divergence， 就是跟它相反。所以 Maxwell 在最开始的时候已经了解到了这些观念的重要性。divergence 跟 curve 都是一个 differential operator。We are going to get to that later。可是，我再念下去。Although Maxwell emphasized the importance of vectors, he never used the vector notation in his papers and books, writing the famous Maxwell equations in clumsy component form. Maxwell's equations 的重要性，我想是没法子来能够解释得清楚的。没有 Maxwell 方程式，就没有21世纪的今天。所有的无线电、电视、网络通信 everything 都是基于 Maxwell 方程式。Maxwell 这方程式是在19世纪中叶他写的3篇文章，这个文章我想是人类历史上最重要的几个文献之一。那么，可是他虽然emphasized the importance of vectors, he did not use it in his papers. So therefore, every equation has to be written 3 times in the 3 components. 是用3个分量。所以你现在去看 Maxwell 的方程式，写出来很不好看，是过了很多年以后才改成了vector notation。 这是谁做的？谁在这里头做的最重要的呢？你看底下这个 page， It was Josiah Willard Gibbs who populated in the 19th century the use of vectors. Gibbs was an American physicist. Perhaps, well, he certainly was the greatest American physicist of the 19th century. Perhaps with Maxwell, he would be classified as among the most important physicists of the 19th century. 他在耶鲁教书的时候，他 emphasized the importance of vectors. 我再念下去。Maxwell did not use the vector notation because he wanted to go beyond vectors and introduced a further mathematical quantity called quaternions, which had been invented by W.R. Hamilton in 1843. Hamilton 是一个大的数学家，一个大的物理学家。你们在念了 more advanced physics 以后，你就会知道有 Hamiltonian， 有 Hamilton-Jacobi equations， 他对于力学的贡献非常大，而他的对于力学的贡献直接影响到量子力学的发展。那么 Hamilton 在1853年想出来了一个数学的结构，他给它起了个名字叫做 quaternion。 他对于这个 quaternion 的发明是非常得意，所以他死了以后，在他走过的一个桥，在那个桥上的时候，他发现了 quaternion， 所以现在那个桥旁边的柱子上就刻着这个 quaternion 的 algebra。 那么 Maxwell 非常佩服 Hamilton， 非常喜欢 quaternion， 所以 Maxwell 就觉得只 vector 不够，他应该把整个的物理学的notation 都改用 quaternion。 因为这个缘故，所以他觉得单是 vector 还不够，要更进一步走到 quaternion， 而他还没有能够把这个更进一步做出来，所以他索性没有引出来，没有在他的文章里头写下来用 vector 的 notation。 所以今天就发现一个现象，他的文章跟他的书都用的是 component notation， 不是 vector notation。 那么这个的影响呢，一直到后来 Gibbs 说是忘记了 quaternion， let us only use vectors， 那个以后才渐渐的发展出来，一直到今天这个 vector notation。 那么 quaternion 是不是就应该被忘记掉呢？这个有一个很复杂的故事，这个故事就是我底下讲的这句话。 For some comments about quaternions and Hamiltonian, please see page 23 of my selected papers. 我在1983年出版了这本 selected paper， 图书馆有，其中有一个 comment 关于 quaternion， 关于 Hamiltonian， 关于 Hamilton。 那么讲到这一点呢，我要给大家讨论一下子。Number system in physics， 在物理里头 the quantities that we talk about are expressed in terms of real numbers. But starting in 1926, up to 1926, only real numbers in physics. Some people might say in 交流电 你们如果在中学的时候学过交流电的方程式，那里头用了 complex notation。可是那个 the usage of complex notation in alternating current theory is not fundamental. It's just a for mathematical convenience. In 1926, it became clear when wave mechanics was developed that in quantum mechanics one has to use complex numbers. So in 1926, in Schrödinger, because of Schrödinger's work, it became clear that one has to use the complex numbers. 关于这个故事呢，你们可以看我的文集。这个我有一篇文章被翻译成中文了，在杨振宁文集里头，这个图书馆也有。你看这个page 636，在那篇文章里头，我描述了在1926年的前后，Schrödinger在发现 wave equation 的时候，他怎么样子在很不得已的情形之下，最后知道非得用 complex number 不可。complex number 在 wave mechanics 里头是 intrinsic， 是内在的，不能够把它取消掉的，跟交流电里头所用的 complex number 性质是不一样的。那么从 real number 到 complex number， 这个观念是数学家引进去的，最初到高斯的时候，大家已经知道应该有 complex number。不过在物理里头是到1926年才了解到，物理里头必须要用 complex number。可是我们如果看这个 number 的 system 的话呢，number system 除了这个 real number 以外，还有 complex number。那么后来呢，就发现有 quaternion。quaternion 是一个非常美妙的算学。刚才我讲 Hamilton 一生认为他最得意的贡献就是他发现了quaternion。那么刚才我讲了Maxwell 跟 Hamilton 都希望把 quaternion 用到物理里去。换一句话说是，既然我从今天的眼光看起来，既然通过Schrödinger工作，我们知道物理必须要从real numbers 走到 complex number 这领域里头，一个很自然的问题就是是不是更应该走到 quaternion 这个领域里头去。这个呢到现在是一个没有解决的问题。不过关于这个问题呢，你看我的 selected papers page 23，我的结论呢是今天 quaternion 还没有真正被引到物理里头，虽然在这方面已经有很多的文章，可是都不是成功的。可是我认为很可能在将来，也许是在座的哪个年轻的人50年以后会发现的，原来 quaternion 必须要引到物理里去。好，现在我们回到 vectors。我刚才讲了半天，其实就是要告诉你们，说是这一个观念在物理里头引进去， 有时候是很复杂的。那么这个 vector 的观念，到了经过 Maxwell 跟 Gibbs， 今天是变成非常重要了。所以你们必须要把这个 vector 的观念弄清楚。这个一个 vector， 这个几何的定义当然大家都懂，就是一个向量。这向量在3度空间的时候有3个分量 ，3 components。那么有时候我们把它写成一个向量 A， 我们写成 AXI 加上 AYJ 加上 AZK。A 的3个分量是叫 AX、AY、AZ，IJK 是 x-axis、y-axis、z-axis 的 unit vectors。那么把这样3个加起来就变成了这个。这个我想你们都很了解的。这个一定能够缩小的。这个关于这个 the addition, subtraction, etc. of vectors is very simple. I'm sure you are already familiar with it. So next I'm going to discuss a concept of a scalar product. It is the dot product.两个 vector A 跟 B 它的 dot product， 这个是在 page 41，你书的 page 41上面。这个是一个 scalar， 是一个 number。这个 number 呢是假如这两个一个是 A， 一个是 B， 这是三度空间呢。那么这中间加这个角，这个角如果叫做 phi， 那么这个东西定义呢，就是 AB cosine phi。是缩小了吗？好。好，谢谢。假如是在这空间的两个呢，你先得要把这两个造一个平面，然后这个 phi 是在这个平面里的这两个之间的角。那么现在我要把刚才这个公式稍微改写一下。A 到 B 也等于 A 乘上 component of B along A。这是 A， 这是 B。什么叫做 component of B along A 呢？就是你从这 B 做一个垂直线。那么这一段叫做 component of B along A。那么这一段的 length 当然等于 B cosine phi。 所以我就有刚才这 formula。这当然也等于 B 乘上 component of A along B。这三个 definition 都是一样的。有了这个以后，我就要证明一个定理，叫做 distributive law。distributive law for dot product， 这意思就是说是 A dot B 加 C 是等于 A dot B 加上 A dot C。这需要一个证明，我这证明很简单 ，proof A dot B cross C B 加 C 是等于根据刚才写的是等于 A 乘上 B 加 C component of B 加 C along A， 这是刚才已经讲过了的。可是 component of B 加 C along A 是什么呢？比如这是 A， 这是 B， 这是 C。注意 A 跟 B 一定是在一个平面里头，这 C 不一定是在那个平面里头，所以 C 可能是翘起来的。But it doesn't matter， 这个 component of B，component of B 加 A 是这个 ，component of B 加 A along the axis 是这一段，这一段你仔细看看，它就是 component of。就等于 component of B along A 加上 component of B of C along A， 同意不同意？那所以就等于 A dot B 加上 A dot C。我要跟大家讲的就是，你要注意，我们刚才讲了一个 distributive law， 这 distributive law 需要一个证明，我刚才给了你一个geometrical的证明。如果 comment 在这个书里头 HRW did not use the distributive law. On page 41, but did not prove it.这是这个书的一个缺点。我很惊讶，因为这个书已经用了很多年了，不知道他们为什么写的时候没有注意到这点。它就是好像是这 distributive law 是很自然的 ，distributive law 是很自然的 ，but it needs a proof, and I had just supplied the proof. OK, once 有了这个 proof 以后 ，we can do the following. A dot b 是等于 axi 加上 ayj 加上 azk dot怎么缩小？好 dot bxi 加上 byj 加上 bzk。现在既然有 distributive law， 所以我们可以把它分开成，刚才的 distributive law 我是写成 a dot b 加 c， 我把 b 加 c 写在前面 dot a 当然也可以。By the way， 我们还可以讲这个 a dot b 当然等于 b dot a。因为这定义是都是一样，是 a 乘 b 乘上 cosine phi。所以你的 distributive law 也可以倒过来写。那么所以你把这个整个展开的话呢 ，you have 9 terms。For example, one term is axi dot bxi. ax 跟 bx are pure numbers, so you get I squared. Now what is I squared? I is a unit vector. So I dot I is of course equal to 1. So therefore this gets ax bx 加上 ay by 加上 az bz。剩下的那些 I dot j、I dot k 都等于0，因为 I 是在 unit vector on x axis，j 是 unit vector on y axis。The phi is equal to 90 degrees. Cosine phi is equal to 0. So therefore, all those dot cross products are 0. So therefore, we get this formula. So we have both a geometrical definition of a scalar product, now an algebraic equation. We could have taken this algebraic equation as the definition. Suppose we took the algebraic expression as the definition. Is that better, or is the geometrical definition better? 你们有没有人回答这个问题？这个 algebraic definition 也可以拿来做 definition， 可是立刻就发生了一个问题，是说这个 definition 如果我不用这个我这个 x y z 的 axis 换一换，那这个 formula 就 look completely different。那所以就有个问题说，你这个 definition， 如果你拿这组 definition， 这个 definition 对于你取得 axis 是什么方向上有没有关系？假如有关系的话，你这个 definition 当然不好。Therefore, if you choose this to be the definition, you have to add a proof that is independent of the choice of direction. You can do that too, but that requires a proof. If you look at it, you will realize that the way we have done it is better. You define it geometrically, then there's no question that it depends on the choice of axis. Then you prove the distributive law. Then you get this formula as a consequence. And then naturally it's independent of the choice of axis because the original definition is independent of the choice of axis. Okay. Any questions about the scalar product? Now we go to definition of vector product. This is on page 42. Suppose a vector A, and here's a vector B. We use A cross B, a vector. With length equal to A 乘上 B 乘上 sin phi， 不是 cosine phi， 是 sin phi。In a direction perpendicular to both A and B. So, 在这图里头一个 A 一个 B， 这个我现在要 the direction of A cross B is perpendicular to the plane, perpendicular to the blackboard. Perpendicular to blackboard 还有两个方向，一个是向外，一个是向内。用 right-handed rule，right-handed rule 的意思就是你在这图上画了一个，你从 A， 因为我刚才写的是 A cross B， 从 A 向 B 这样子转，然后你的大拇哥的方向。假如这个是这样，假如这个 phi 是一个钝角，还是一样的，还是从A 到 B 向外边走。Does everybody understand this definition? Okay. Immediately we are going to write down a formula. A cross B is equal to minus B cross A. Why? Because if you take B cross A, length is still the same. It's B times A times times sin phi. Did I say sin phi or cosine phi? Times sin phi. So that's not changed. But you have to take your right hand and go from B to A. So it goes inward. Therefore it's equal to minus A cross B. Furthermore, A dot A cross B what is this? 0. Because A cross B is perpendicular to A. Therefore, the angle between them is 90 degrees. So by definition of dot product is 0. So this is equal to 0. Also is equal to I also want to write down the following formula. A cross B the length 这个 notation 书上不用，我常常用的就是它的 length。这 length 是等于什么呢？等于 A 乘上 B 乘上 sin phi。可是 A 乘上 B 乘上 sin phi 是等于这 parallelogram 的 area。你画一个平行四边形的话，这个的 area 很显然是 A 乘上 B 乘上 sin phi， so therefore 等于 area。Questions? at this point, I want to point out that the book makes another mistake. Namely, the book uses at the bottom of page 42 the distributive law without proving it. The distributive law for vector product is this: A cross B plus C is equal to A cross B plus A cross C. This requires a proof. This proof is somewhat more complicated. Again, let me say, here we are going from a geometrical definition through the distributive law to arrive at the algebraic expression. You could have started with the algebraic expression as the definition, but then you are left with the problem of proving that that expression is independent of the choice of axis. And that is a much more complicated thing. Without that proof, the definition, algebraic definition, is not useful, because how do you know that the result is independent of the choice of axis? Now this proof is a little bit more complicated. Step one, I'm going to introduce a notation. I'm going to write A cross B as A cross I'm going to introduce a notation B sub A. B sub A is defined to be the projection of B perpendicular to A. In other words, if this is A, this is B,这个 B 一部分是 parallel to A， 一部分是 perpendicular to A， 这一段我叫做 B sub A。 Is that clear? Sorry. .为什么我可以写这个呢？因为 first, the length of by definition A cross B is equal to the length of A times the length of B times sine of phi. The length of A cross B sub A is equal to the length of A, the length of this, which turns out to be B sub B sine phi, and it's in the same direction. So therefore there's this formula. Okay, with that we are going to now calculate A cross B plus C. By definition, this therefore, using what we just said, is equal to B plus C A. I'm just copying the equation 1. But I now claim that this is equal to, this satisfies distributive law. This is a little bit complicated. now I'm going to project everything in a plane perpendicular to A. So think of A as pointing toward you. And I'm going to write B, A, C, A. So A is perpendicular, pointing toward you. BA is the perpendicular component of B relative to A. Refer to the earlier diagram. And CA is similarly the projection of C, the component of C, which is perpendicular to A. I'm going to write down A cross BA. What is A cross BA? A is toward you, cross BA. So therefore, it is perpendicular to BA and goes this way. That's A cross BA. It's perpendicular to BA. Its length is equal to A times the length of BA times the sine of the angle between them. But the angle between them is 90 degrees. So therefore that's 1. So therefore this red line, the magnitude is equal to A, the length of A, times the length of this. Similarly, I can write down a perpendicular to this one. This is perpendicular to this one. And this is A cross B, CA. Right? This one is CA. Now, what is BA plus CA? BA plus CA is this. What is A cross? This is BA cross CA. Plus. What is A cross this thing? It's something perpendicular to it. That is A cross B, BA plus CA. Now you see that this you get another red parallelogram. This red parallelogram 这个 project 出来没有颜色是不是？在我这上面是有颜色的。有颜色。OK。我直接讲一下。你把这个图仔细看懂了以后，你就会懂我底下要讲的这句话，就是 这个东西是等于So we have proven the distributive law for vector product. I want you to review carefully that diagram, that complicated diagram, and understand this proof thoroughly. Okay, with that, we can now have an important formula, algebraic formula. For vector product. Namely, A cross B is equal to AXI plus AYJ plus AZK cross BXI plus BYJ plus BZK, and that's equal to, now using the distributive law, we have 9 terms, but I cross I, what is I cross I? Is 0, because sine phi is 0. So all the I terms are, so there are only cross products which are not 0. Now I cross J, right here, I cross J is equal to K. Obviously, I is the unit vector along x-axis, J is the unit vector along y-axis. If you take the product, the lengths are both equal to 1. The angle is 90 degrees. Sine phi is equal to 1. So therefore it becomes unit vector along the z-axis. So I have this, and of course cyclic permutation. J cross K is equal to I. K cross I is equal to J. Cyclic permutation. This is a common notation. CP means a cyclic permutation. That means you write down this equation, and it's true also with the cyclic permutation. Cyclic permutation meaning J replacing I, K replacing J, I replacing K, in that order. Okay, so now it becomes obvious that J cross K will give me I, so therefore I get AY BZ minus AZ BY times I plus AZ BI BX no AZ BX minus AX BZ times J plus AX BY minus AY BX times K. So the 9 terms becomes 6 terms, and they are combined in this fashion, which is equal to a determinant. Well, I have a tendency to underline I, just forget about it. I don't need to underline. Right? That determinant, if you expand it, by the way, if you do not remember or have never studied the determinants, go back and study it. It's extremely important, and you have to be very familiar with the determinant. Now, according to the determinant, if you expand it according to the first row, because I times this 2 by 2 determinant, which is AY BZ minus AZ BY, precisely like this. So So we have now proven this formula, which is very important. By the way, we had earlier said A cross B is equal to minus B cross A. That is very obvious if you use this formula, because if you switch A and B, you are switching two rows. Switching two rows of a determinant, a fundamental theorem is that it changes the sign of the determinant, etc. Another one. What is A dot A cross B? If you do A dot A cross B, that means you remember A dot something. You take two vectors. You take the x component of this times the x component of this plus the y component of this times the y component of this, z component of this times the z component of this. You add those three terms. So if you do it here, it is equivalent to replacing this I by, if I now wanted the A dot A cross B, all I have to do is replace ijk by ax, ay, az. Then you get a determinant which has two rows which are identical. Another theorem says if you have a determinant with two rows identical, it's equal to 0. So that's another proof of A dot A cross B equal to 0. So is everything crystal clear? Am I going too fast or am I going too slow? Okay, let's vote. Who wants to say I'm going too slow? Who wants to say I'm going too fast? Most people have no opinion. I think you are too shy. I assume that everybody has understood everything. If you have not completely understood it, okay. For those people who think that I'm going too fast, which particular point you want me to explain again? 不要害羞，你什么地方没懂，你现在问，还是都懂了？ Yes.
I just see the last page of your paper. Last page. 上一张纸啊。
哪个 page？
Yes, 我想请教一下，就是，从这一步到这一步，这个时候证明是用这个图形来证明吗？是用刚刚这张纸上的那个矢量图来证明吗？
对。对。对。
是用这个来证明
对
这一步过程吗？
对。
这个是通过显然的一种看法。
是很显然的。那这个同学问我，就是刚才。 不要，刚才这几步里头，怎么证明？就是说看这个图，这图里的关键的一点就是这个红的这个平行四边形，就是这个蓝的平行四边形放大了一点，转90度。 你如果把这个观念弄清楚了，你再回去看这个，你这每一步都是对的。这个假如还有问题，你回去仔细研究一下。比如我举个例子讲，假如 a 的 length 是等于1，那这个红的就跟那个蓝的完全一样，只是转了90度，因为每一个 length 都乘上1，那当然就等于就是原来的。假如是 a 是等于2，它就是放大了1倍。你把这个图弄清楚了以后，你就知道这每个 step 都是对的。OK， 假如大家没有问题，假如大家没有问题，我回到这个刚才讲这个quaternion，我想你们这里头对于数学比较发生兴趣的人会对这个我底下要讲的会觉得很有意思，因为这个数目是我刚才讲了 starts from actually one starts with integers. Then, because one wants to divide, so one gets into fractions. But from fractions, we got into irrational numbers, namely all real numbers. Does everybody know when people began to realize that they are irrational numbers? Does anybody know whether there are more a rational number is a fraction? A irrational number is a real number which cannot be written as a fraction. This is not the correct definition, but it's a definition that everybody would understand. Does anybody know, are there more real numbers, are there more rational numbers, or are there more irrational numbers? Why? How do you know that there are more irrational numbers? This is a question which was only resolved in the 19th century. It follows a rule called the diagonal rule. If you read some popular mathematics books, it will explain to you, using the diagonal argument, you can prove that there are many, many more irrational numbers than there are rational numbers. And that line of mathematical development became very, very important and became that led to the science of mathematical logic. Mathematical logic was one of the most important subjects in mathematics around the beginning of the 20th century. And Hilbert, who was the greatest mathematician, perhaps with the Poincaré, the two greatest mathematicians around the year 1900, devoted much of his effort to mathematical logic. But does anybody know what happened to mathematical logic afterwards? Hilbert's program was proven to be impossible by a young PhD candidate. Have you heard of this person's name? Gödel. I think Gödel not only is the greatest mathematical logician, one must agree that he is one of the greatest thinkers in the history of mankind, because he proved that the kind of Hilbert project, which wanted to put all mathematics along the style of Euclid's geometry, is impossible. That caused a revolution in mathematical thinking. After that, there was a young British number theorist called Turing, and then there was von Neumann. Turing and von Neumann were working in mathematical logic, and these give rise to the modern computer. And the influence of modern computer, of course, is something that I'm sure all of you realize. Von Neumann and Turing both made major contributions to this. For example, Turing invented the idea of a universal computer. What he proved is that all modern computers, if each of them has infinite memory, if you do not worry about the time, then they are all equivalent. What can be done by one computer can be done by another computer, and can be done by his computer. His computer is called a Turing computer. In order to honor him, there is an international prize called the Turing Prize. It is the highest award in software theory. And I'm very happy, and I'm sure you would be very happy to know that Professor Yao Qizhi Andy Yao has now become a professor at清华. He won the Turing Prize a few years ago. It's equivalent to the Nobel Prize in software theory. And all of this follow a kind of a reasoning about the logic of mathematics and the definition of numbers. And if you follow that line of argument, one branch would lead to the idea that there are real numbers, there are complex numbers, then the next one is called quaternions. It can be further proven. This proof is not, it's long but not difficult. I'm sure every one of you can understand it if it's explained to you in detail. These three, each of them is called a division algebra. A division algebra is an algebra like a complex number. The complex number system is a division algebra, meaning you can add, you can subtract, you can multiply, and you can divide by any number in that system which is not zero. For the real number system, you can certainly add, subtract, you can multiply, and you can divide provided the denominator is not zero. The complex number has the same property. So the complex number system also is a division algebra. It is proven that there is a third one, and only a third one, called quaternions. The quaternion system has a system of numbers. It's a generalization of complex numbers. And there you can add, subtract, and divide multiply and divide provided the denominator is not 0. And you can prove that there are no more. But there's a difference between complex number, real numbers and complex numbers as contrasted with quaternions. Multiplication is commutative in complex numbers. A times B is equal to B times A in the complex number system. But A times B is not equal to B times A in the quaternion system. So real numbers and complex numbers are commutative in multiplication. But quaternions are not commutative. In multiplication. Now in physics, originally every time you want to multiply two quantities, because they were real numbers or complex numbers, it's commutative. But with quantum mechanics, we now know that quantum mechanics is based on an algebra which is not commutative. So after quantum mechanics was developed, physicists realized that you not only have to use real numbers, you have to use complex numbers. You not only have to deal with an algebra which is commutative, you have to deal with algebras which are non-commutative. Therefore, it became much more acceptable to imagine that perhaps the number system that we are using today need to be broadened. Now, after having told you so much about the quaternions, I think I need to give you a little bit of details about it, especially since we still have some time. A complex number system deals with A plus BI. A quaternion system deals with A plus BI plus CJ plus DK. It has three imaginary numbers, I, J, K. The multiplication rules is I squared equal to J squared equal to K squared equal to minus 1. Ij is equal to K is equal to minus Ji, cyclic permutation. This now defines the quaternion algebra. So you now know how to add and multiply. But the question is how to divide. The theorem is this. Q, the inverse of Q. Inverse of Q is the number which multiplied by Q, either in front or in the back, is equal to 1. This is equal to you see that this is very similar to complex numbers. With complex numbers, the inverse of a complex number is equal to the complex conjugate of that number divided by the absolute value squared of that number. This is just a generalization of that. So you might say that why did Hamilton choose only IJK? Why not just IJ? Why not IJKL? These need proofs. It turns out, for example, if you cut off and try to invent some rules for multiplication of I and J, you can prove that it would not work. It's only when you have 3 that You have three imaginary numbers satisfying this rule that this is a division algebra. This is a beautiful theorem which is not proven by Hamilton. Hamilton only invented this algebra and proved that you can divide. But later it was proven that if you want to have a division algebra, there are only three. There's a real number, complex number, and quaternions. As to why there is the hope or the expectation that quaternions would enter into physics, I cannot give you any details, but if you read my selected papers, I think it's page 23. I have some comments about that. I assigned 12 exercises. I want you to hand them in next Monday. Don't be late. I went faster than I thought I would. So I proposed that we do the following. I'll sit here and we'll stop the lectures, but you can individually come and ask me questions in the next half an hour. Okay, goodbye.我们以后常常见面，所以请大家不要拍手了。